my great honor to introduce Professor Luiz Davidovich. The reason I get the honor is because I've known him longer than anybody else in this building, probably even this city, because his wife is probably in some other city right now. Luiz is a man among men. Luiz is the Secretary General of the World Academy of Sciences. I repeat that, Secretary General of the World Academy of Sciences. Recently, he's given an address to the United Nations on the issue of pollution in cities and the fact that it kills more people every year than COVID. But Luiz came to us in New Mexico. He was a brilliant young lad. We all knew that. But what endeared us to him, in addition to his brain, is his sense of humor. I will give you one example. We are always getting these messages about whatever, sexual awareness. You must not abuse anyone, right? And in those days, making eye contact was abuse. So in comes this bright young postdoc to my secretary, and he says, "Would you type this for me?" That note, thank you for being with us today.
Thank you, Marlon. You don't need this?
Yes.
No.
Oh, yes, yes, yes.
Yes, 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 okay. Okay, so you see, it's an honor for me to have been introduced by a great hero of quantum optics, laser physics, and lots of other things. So it's, you know, actually, I knew Marlon much before I met him because I studied in his book on laser physics, and I followed his papers as well. So it's a great honor for me to be introduced by him, and I'm very happy to be here again. You know, I come to College Station, to Texas A&M, half of the year, 4.5 months each year. And the other time of the year, I am at the Federal University of Rio de Janeiro, and I always look forward to coming here and interacting with this amazing group of people at the Department of Physics and Astronomy at the Institute of Quantum Science and Engineering of Texas A&M. So it's a great pleasure for me to be here. Now, I presented a colloquium in December, I think, of last year, on the classical limit of quantum mechanics, and of course, you know, it was expressed, right, that, you know, it was told me that I should not repeat it, of course, and I'm not going to repeat it. So I thought, so I will talk about something else. And in fact, there is a small intersection with the other colloquium, I think 3 slides only, from a total of 300 slides. So it's a very small thing. And of course, I'm quite aware that eventually you want to go to sleep. So I hope to allow you to go home before sleeping time, okay? So what I'm going to do is actually to tell you about a thread in my career, say, which involves cavity quantum electrodynamics and quantum measurement. It's not the only thread, but, you know, as I was preparing this colloquium, I saw the connection between the several theoretical developments and experimental developments with which I was connected. So I'm going to tell you about this thread. There are other threads too, regarding laser physics, for instance. There was a strong collaboration with Marlon and his group. But today I'll focus on this thread. And I'm not going to tell you either about, as you saw in the abstract, about cavity quantum electrodynamics in general, what the several groups in the world are doing about that. It is going to be a biased presentation because I'll tell you about my experience in this field, okay? The things, the work I have participated in. So first, let me give you some introduction to cavities, since we are going to talk about cavity electrodynamics and the atoms that are used in these experiments. Now, cavity electrodynamics, I would say that really originated from the work of these two giants, Serge Haroche and Walter, in the microwave domain. In the optical domain, the great work of Kimball, and then Rempe was also a hero in this field, and then many other people came. Now, these are the orders of magnitude for the cavities I'm going to talk about. This cavity is built with two excellent mirrors. In fact, they are the best mirrors in the world. They are made with copper covered by a layer of niobium, and they are kept at very low temperatures, 0.8 Kelvin. They are in the superconducting regime. This is a sample. This is actually the half of the cavity. You see the lower mirror here, and you have here an insertion for the upper mirror. And these things you see here, these are piezoelectric moved things that can actually adjust the upper mirror. Okay, so it's a way to adjust the upper mirror in a very sensitive way. So that's the system. That's the last system that was built. There was a report on it in this paper here in 2007. And this cavity has amazing properties. Well, this is the frequency of the mode of the field that is used in these experiments. That's the coupling between the atom and the field in the cavity center. And this mode here has a Gaussian profile. The waist of this Gaussian mode is equal to 6 millimeters. And this distance between the centers of the mirrors is about 30 millimeters. The borders here are separated by around 1 centimeters. And the damping time of these cavities is 130 milliseconds. Now, if you multiply the frequency of the field in the cavity by the damping time, you find this result here, which is an amazing result for cavity grading. Okay, so it's 10 to the 10. And when I started to collaborate on this with the group of Serge Haroche in Paris, I once gave a talk there, and I said in that talk that 10 to the 10 would be possible, and then someone in the audience said that's impossible, no? Because the theory shows that that's impossible. and now that's the value. Okay, 10 to the 10. It's an amazing work of engineering. Actually, here you have some guards, you see, on the side that help to increase the Q of the cavity because they don't allow the photons to escape from the sides. And the atoms come in this direction. You see, it's a huge hole here, so that they are not changed by the electric field between the two mirrors. Okay, when they come into the cavity. In fact, you can apply a voltage between the two mirrors. So there is an electric field there, and this electric field stabilizes the atom as they go to the cavity. And also it allows to change the distance between two levels of these atoms. So you can go from resonance to dispersive, non-resonant behavior and so forth. Okay, so it's a fantastic work of engineering. Okay? Now, as for the atoms, the atoms that cross this mirror, there is the atom crossing. I'm very proud about the simulation. I hope you enjoy it. It took me a long time to do it, more than writing the slides, certainly. Anyway, so I'm very proud of it. So, you send an atom then through this cavity. In this picture, the atoms go this way. And these atoms are Rydberg atoms. They are huge atoms. They are alkaline atoms, rubidium atoms. And you take the valence electron to a principal quantum number equal to 50 or 51. Okay? So that's like a hydrogen atom, because there is this valence electron that's far away from the nucleus. So it's a huge atom. In fact, you see the transition dipoles, so related to this external electron in the nucleus, is of the order of 1,000 atomic units. Okay? Now, also, the angular momentum of the states is equal to the principal quantum number -1. This is the maximum value allowed for the angular momentum in a hydrogen atom. So this means that you have circular atoms. So this electron is in a circular orbit, far away from the nucleus. Now, because the electron is far away from the nucleus, also the radiation of this electron, classically would be small. Of course, quantum mechanically it's an orbit, so there's no radiation. But the lifetime is 30 milliseconds, which is a large lifetime, compared with the lifetime of usual atoms, which is what, 10 to the -8, 10 to the -9 seconds. So these atoms are sent through the cavity with an average speed of 250 milliseconds. They are produced by an oven, actually, an oven. Okay? They come as a beam of atoms. And the transition frequency between these two levels here is 51 gigahertz. The effective interaction time between these atoms and the mode is 30 microseconds, which is nice because you see this is much smaller than the lifetime of the atoms. It is also much smaller than the damping time of the field in the cavity. Okay? So this allows one to send these atoms through the cavity and, in principle, neglect damping from the field and the atom. At the end, you must make some corrections, but to begin with, you can neglect that. So this is then the system we are going to discuss in this talk, and I'm going to show you several examples of some very nice things you can do with these systems, which are related to really to the foundations of quantum mechanics, to fundamental concepts of quantum measurement. Okay? So we are going to use the so-called dispersive interaction between the atoms and the field. And let me tell you how to the effects of a dispersive interaction in classical physics. Suppose you have a cavity here with some field inside. So you have these boundary conditions at the end of the cavity. The field should be 0 here and here. And now you introduce into the cavity a slab, transparent slab of some material with some refraction index. Now, before introducing this slab, the wavelength of the field in the cavity is given by this famous expression, speed of the light divided by the frequency of the field. Now, as you introduce the slab into the cavity, the speed of light will change, right? Because it changes because of the material you introduce in the cavity. And since lambda cannot change because of the boundary conditions, that means that the frequency of the field should change. Okay? Now, if you introduce the slab for some time and then you take it out, well, while it was there, the frequency of the field was changed. So as you take it in and take it out, what's going to happen? The phase of the field will change because of the introduction of the slab. It will not rotate as it was with the free cavity. And now with the slab, it's going to have some difference in phase, okay? So by introducing the slab and then take it out, you can change the phase of the field in the cavity. That's classical, okay? Now let us look at the correspondent quantum mechanical description of it. So now we have an atom, which is a Rydberg atom. And what I'm going to show you is that a Rydberg atom is so huge that a single atom can have an important refraction index and can change the phase of the field in a very important way, okay? So we assume we have in the cavity, that big cavity of superconducting material, a coherent state, which can be expressed in this term, with this formula, in terms of Fock states, which are states of the field with well-defined photon number. So this is the closest we can go to a classical state, okay? It's a coherent state. Now, we consider that the atom has actually 3 levels important for these demonstrations here. They are close to the frequency of the mode in the cavity. And this is an excited state. This is a ground state. Actually, this is not necessarily the ground state. These two states could be excited states of the atom, one lower state and another upper state. And there is an intermediate state here in such a way that state E and state I are not resonant with the cavity field. This is off resonant, which means that there will not be a transition between these two states, but the phase could change. So the atom is then not resonant with the cavity field, but it could induce a phase shift. Let's see how that happens. So this is the system containing the atom in the excited state, or this upper level state, and the coherent state. So I just multiply the state of the atom by the state of the coherent state, and you get this expression here. Now, because of this interaction with the cavity field, this state becomes transformed into this one. You get this extra factor. And let's understand this. Okay, this extra factor depends on the number of photons in the state. In fact, this is just the Stark shift of the state E. The Stark shift is proportional to the number of photons in the state. So this is Stark shift displacement due to a dispersive interaction between atom and field. Now, you see that here we have a power of n in this exponential. We have another power of n in this exponential. So we could put this factor together with alpha and let them together get this power n. So you see that now, if I put this together with that, I have also a coherent state as before, but with a change. Instead of alpha, I have alpha times e to the minus I phi. Okay, so in the expansion, you get this e to the minus I n phi. So you see that the interaction of this state E with the field in the cavity resulted into a phase shift of the field in the cavity. And this is the quantum reasoning corresponding to the classical phase shift analysis due to the introduction of that transparent slab with refractive index in the cavity. Now this phase here is what one calls phase shift per photon. It's given by the coupling constant between atom and field divided by the detuning delta multiplied by the interaction time. Okay, so the longer the interaction time, the larger will be the difference between the rotation of the state with the atom inside and the rotation of the free state. And this is then the phase shift per photon. Okay, so that's the quantum version of what I showed you before. The atom works as a refraction index, but I'm talking about a single atom doing that. Now, how can we use this? Well, first you can use this considering atoms and photons as qubits. So, of course, if I consider two-level atoms, an upper level and a lower level, the atom can be here or there, and this is a qubit. So I can call E the state 1, G the state 0. Now, if, on the other hand, so the atom can be in general written as a superposition of these two states. On the other hand, if I have a cavity with 0 or 1 photon, that's also a qubit. And I could have the cavity in a superposition of the two states. So we have here two qubits. And of course, I have to measure them. How do we measure the atom when it goes through the cavity? You see, I like this. So you let the atom after it goes through the cavity through this ionization chamber. You see that the ionization chamber has this funny aspect here. What's happening is that the electric field here is larger, smaller than the electric field here. So if the atom is in the E state, it is ionized when it goes through this region here. If it is in the G state, it is ionized only when it goes through this region here. So if you have an oscilloscope connected to that, you see two peaks, one peak or the other, depending on the state of the atom. So that's a way to measure the state of the atom. Now, how can you measure the state of the field? Well, you let the atom go to the field, and then you measure the state of the atom. Okay, so that's the idea. So you have two qubits, and you can measure all of them. Now, with that, we can do what people now in quantum information call gates. Okay, so let me show you how you do a phase gate with atoms in this cavity. Well, a phase gate is defined by this expression here. You see, it tells me that if the first qubit is in state 0, nothing changes with the second qubit. So 0 for the first qubit means that if the second qubit is in state 0, it will remain there. If it is in state 1, it will remain there. However, if the first qubit is in the state 1, then if the second qubit is in state 0, nothing happens to the state. On the other hand, if the second qubit is state 1, there is some phase here, a pi phase. So you have a minus sign showing up there. How you can implement a phase gate with cavities? Well, if there is, you send an atom to the cavity. If there are 0 photons in the cavity, well, nothing happens. Okay? So again, this is this property here, the first line. Now, suppose there is 1 photon in the atom, in the cavity. Well, then, of course, the upper state can be resonant with the cavity. And then if there is 1 photon in the cavity, we calibrate this interaction so that the atom goes to this intermediate state and then goes down. So that's what one calls a 2-pi pulse. Okay? It's a 2-pi pulse. Now, the 2-level atom behaves as a spin in this case. Oh, I had a cup here with a coffee, but it disappeared. But anyway, I can do it with this. So, you know, it's a 2-pi evolution. A 2-pi evolution changes the sign of the state. You need a 4-pi evolution to get back to the same state. That's a proper of 2-level systems, like a spin or a 2-level atom. There is an analogy, please. This is just an analogy between that and some topological problems. For instance, I take this can here and I do a 2-pi rotation. Oops, it's not in the same state, but then I continue. I do a 4-pi transformation and then I go back to the original state. Okay? Students, don't try to do that without training, okay? Because you could do something bad to your arm. So be careful, okay? Now, so we use this property here, and it's actually better to do this because it's a resonant transition than do a dispersive interaction in this case, because resonant transitions are stronger than dispersive transitions. So this was implemented in this paper here in 1999. That was Serge Arocha's group. And I guess I'll just jump on that. That's a scheme for this logic gate. Now, I want to show you now how these notions can be used to discuss quantum measurements. So this slide I showed you in last December. I have here a measurement. So suppose the atom is in the upper state, then this pointer goes right. If the atom is in the lower state, the pointer goes left. Now suppose the atom is in a superposition of the 2 states, then since quantum physics is a linear theory, this should give me this kind of state. Okay? So if the pointer is in this direction, the atom will be in this state, perhaps in the modified state psi1, because it could be changed by the interaction. If it is in this direction, then the atom will be in the psi2 prime state. And so you have here what we call an entangled state between atom and field. Now, of course, I could just call this a new state of the measuring device. It's a device with 1 more atom. And this is a superposition of 2 macroscopic states of the device with different positions of the pointer. Now, I talked about this last December. I'm not going to discuss this, but of course, I cannot resist to point out that this is like a Schrödinger cat, okay? It's a coherent superposition of 2 macroscopic systems. In this case, the cat is a measuring device, which is so that I'm safe with respect to the societies that protect animals, okay? You know, this is a physical device, it's not a cat. Now, so let me show you how we can use these devices to measure the parity of a field in the cavity. And I'm going to use this afterwards for some interesting demonstrations of quantum mechanics. So here I have a system in which we have this very high Q cavity, and then there are 2 other cavities here, which don't have a high Q. and this setup is typical of Ramsey interferometry. Now, the idea is the following. You send an atom through the system, and then you detect the atom, but you do some things to the atom. When it goes through this cavity here, since the cavity is a cavity of low Q, there is an electric field here, which for the atom is like a classical field. So what this field does to the atom is to rotate the atom in atomic space. So if you think about that as a spin, it takes the spin up and puts it in the equator, okay? So it becomes now an eigenstate of Sx, sigma x. And then after doing that, this atom goes to the cavity. Now this atom interacts dispersively with the cavity field, in such a way that the phase shift per atom is pi, okay? So if the atom in state E, the phase of the field will change to minus alpha, minus, so we have here coherent state minus alpha. If the atom in state G, you just have the state alpha, nothing happens to the state of the field. Now, so now you have an entangled state between atom and field. And if you remember that picture on the quantum measurement, Schrödinger cat picture, we can consider this a quantum measurement as the other one. In fact, the phase of the field is the pointer for the state of the atom, right? If you measure the phase of the field, you know what the state of the atom is. But here I'm going to consider something different, a twist of this idea. I'm going to measure the state of the atom, and with that, I'm going to interfere with the state of the field. Of course, if I measure the state of the atom after this interaction, nothing fantastic will happen. If I find the state of the atom excited, then I know that the phase of the field is minus. If I find the atom is in the state G, the state of the field is alpha. Now, there's something better that we can do, is to apply another classical field to these states and apply this transformation. And now from this state here, I get this state here, which becomes more interesting. Okay? So you see that if I measure the atom in state E, using this device here, the field is projected onto a superposition of two coherent states. Same thing if the atom is found in the state G. And you see that if you look in detail to this superposition, the coherent state, as I showed you before, is given by this expression. So if you find the atom in the state G, you have a sum of alpha and minus alpha. And this sum here, because of this minus sign here, will mean that you only have even contributions in this sum. Okay? So measuring the atom in state E is equivalent to a parity measurement of the field. And as quantum mechanics tells us, if you make a measurement of parity, at the end, the field will be in a parity eigenstate. Okay? So of course, if you detect E, then you'll have an odd parity. So this is a parity measurement of the field. And because it's a parity measurement, if you send now another atom to the system, guess what state you are going to find it in? Same as before, right? Because the first atom projected the field onto a parity eigenstate. So the second atom confirms that, okay? It's the same parity eigenstate. Now, of course, if you had dissipation, things could become different. Decoherence would mean that you have not just an odd parity state or an even parity state, but new Fock state will show up in this superposition, and then this story will be destroyed, okay? So you could get different states for the second atom, which means, of course, that sending the second atom is a way to measure the decay of the field in the cavity. But I told you last time, so I'm not going to tell you now about that. In fact, today's colloquium will assume that decay can be neglected. Okay? It's the opposite of the colloquium I did in December, where the decay was very fundamental for explaining the transition from quantum to classical physics. So now, with this in mind, let me tell you now how we can make a very interesting measurement using these devices, which is called a quantum non-demolition measurement. Well, there is a nice review of that done by Braginsky in Science in 1980. Those who are interested, I advise you read that, okay, Braginsky was a great pioneer in this field. He was an experimentalist doing fantastic measurements, very sensitive measurements in Russia. And the purpose of the quantum non-demolition measurement is the following. You want to measure an observable of a quantum system. For instance, could be the energy or the photon number of a field, by detecting a change in an observable, in another observable, which I call P from probe, which is coupled to S during a finite time T. Okay, so you couple that probe, and you want to detect a change in this observable, and this change will lead you to measure this observable. But there is a strong condition that this measurement should not perturb the subsequent evolution of this observable. In other words, the idea of quantum non-demolition measurements is that the collapse state, so the state after the measurement, is invariant under the system's unitary evolution. Okay? Now, example, consider, for instance, a free particle. That's the Hamiltonian of a free particle. And suppose I want to measure the position of the particle. Now, if I measure the position of the particle, Heisenberg uncertainty principle, I will destroy the certainty about the momentum. Actually, I will change the momentum of the particle. And if I change the momentum of the particle, that means that the further evolution of the position will change because the momentum changed. On the other hand, so this is not a non-demolition measurement, it's two no's. So it's a demolition measurement. Now, of course, you could also measure the momentum. Now, if you measure the momentum, then you destroy the certainty on the position of the particle. But you see, the position of the particle is not present in the Hamiltonian. So this will not affect the further evolution of the momentum. Okay? So the momentum will stay there as you found with the measurement, except for further interactions with the environment. Okay? So that's the idea. For some, depending on the Hamiltonian, for some observables, you could have, in principle, a quantum non-demolition measurement. But of course, here, we are especially interested in cavity QED and photons. And in principle, looks like that the quantum non-demolition measurement of light is a challenging task. Because photons are detected with photon-sensitive devices that usually absorb them. And then there's no photon anymore. Okay? So that's photon demolition, not to say, but the photon is out. So how can you do that? Well, in the things I told you up to now, there's a clue to that, because I told you about dispersive interactions. And dispersive interactions imply that the atom gets its states shifted, but there is no photons coming in and out, okay, from the atom. Okay? So it does not change the photon number of the cavity. So that's the idea. We're going to consider non-resonant processes and consider that these processes have a nonlinear dispersive effects in a medium. So, question, okay, that looks like an interesting idea. Now, could one use this to pin down photon numbers, including a single photon? Of course, if we're dealing with single photon, we need extremely strong light-matter coupling, which means we should confine the field in a cavity. Okay, so that's the idea. Let's use a cavity, non-dispersive interaction, and let's try to see how we can do a quantum non-demolition measurement. So if you are in this limit, then I can write down the Hamiltonian of an atom interacting with this field in this way. This is the transition frequency between two levels, considering a two-level atom. This is omega 0 is the transition frequency. And now this is the phase shift, which I mentioned before, the energy shift of the atom due to the interaction with the field, dispersive interaction. Okay? So I replace here the photon number by the number operator, which is A daga A, and this S here stands for system. Okay? That's the system I'm trying to measure. Now, So this happens, of course, if the atom is in the excited state. I'm taking the energy of the ground state or the lower energy state to be zero. Okay, it does not interfere with this measurement. So now this is the projector onto the excited state, and I can write that in terms of the Pauli sigma z operator like this. Okay? This is completely equivalent to that. Now, I use a probe to observe the system, the x component of sigma x. That means that I'm not going to measure the spin along z. No, you can always think about the two-level atom as a spin. So I don't want to measure the spin of the atom along x. Okay, so that's the probe, and we can show from this Hamiltonian that during a time interval t, the phase of this probe here increases by this amount here. I leave it to you as an exercise to the students. Okay, it's not simple problem. Okay, so you see the phase changes, of course, because of this energy, this frequency here with t, but then there is this phase shift here. So if you have n photons in the cavity, the phase will be given, the phase change will be given by this expression. That's the Stark shift. Okay? So you see, that means that the phase associated with sigma x depends on n. So the measurement of the phase could be used to find n. Okay? So that's the idea. Okay? Now, we can show that this satisfies all Q and D criteria, because you see, when you measure the number of the photon number, you scramble the phases. And we're going to see soon that, okay? So the phase is changed, but the phase is not present in this Hamiltonian. So it does not interfere with the subsequent evolution of the photon number, okay? And you can see that all criteria for Q and D are satisfied by this interaction. Okay? Very simple interaction in principle, okay? And now we are going to see how we can do an experiment that measure this. Now, so again, cavity QED with a more sophisticated picture. You see, here is the oven. The atoms come out of the oven, say in the upper state of a Rydberg atom. And then when they pass through this cavity, they are put in this state here, which means that the spin has changed to Sx, okay? So this is the state of the atom. It's a coherent superposition of the upper state and the lower state. Now, you see this coherent superposition means that you now have a spin along the equatorial plane in the, say, block sphere, with the sphere that characterizes the spin. And this spin now has a polarization, if you want. There's a dipole moment of the atom, which is described here. If you sum this wave function for state E with the wave function for state G, there is an interference between them, and the final wave function is given by that. It's asymmetric, and this represents an atomic dipole that rotates in the equatorial plane, like a spin, for instance, with a magnetic field. Now, this goes now through this cavity. So this is the atom, this is the cavity field. And as it goes through the cavity, it has a dispersive interaction with that, so that if the atom in state E, there is this phase shift here. So we get a state like that. Oh, there is a sum of n missing here, okay? Sum of n missing. So this is an entangled state. So and now the atom goes out of the cavity. We have this state here. But remember, we want to measure sigma x, right, at the end. That's the probe. How do you measure sigma x? Well, you turn the spin again so that it is on the z direction, and then you measure sigma z. It's equivalent to that, okay? The length of the spin doesn't change. The projection of the spin doesn't change. You just rotate so that it goes to the z-axis. And therefore, that means that you have another transformation like that, which is practically you undo what you did before, something like that. And then you get a state like this. And now you see that the probability of finding the state E or G is given by the magnitude square of these coefficients. So the probability if there are n photons in the field is given by this expression. And this is the expression I'm going to discuss now. It's an interesting expression, you see, because this magnitude of Cn squared is just the probability of finding n photons in the field, right? So I'm multiplying now this probability by this other probability of finding the atom in the state E or the state G, which is the magnitude square of these two coefficients. So you see, you have now a different probability distribution, which is modulated by this cosine term. Now, let me show a picture that shows that. Suppose you have an initial distribution, which is like this. That's a distribution of photon number in the field. And then suppose I find the atom in the G state, then you have to modulate this distribution by this factor here. Now you see this is an oscillating modulation. So actually for some values of n, you could get here -1, so Pg of n will give 0, okay? So that means that the probability of having n photons if you found the state G, for some n's will change, will get to be 0. And in fact, from this distribution, you get this one here. And you see that there are some zeros here, which means that by measuring the first atom, you decimate the population for that value of n, depending on whether you found G or E, because these are two different functions. So your job of finding n has become simpler because now you have less Fock states to deal with. Now, of course, you still have many Fock states here. You see, I'm measuring the population. And the first atom reduced the amount of values of n that I can have because it decimated some of them. Now, I send another atom. In fact, what I can do, for instance, is to change this epsilon. This epsilon is phase shift per atom. It depends on the transit time between the atom and the field, and also on the tuning between the atom and the field. So I could change this epsilon, and by doing that, I could, compress or extend this curve and have other ends deleted. Now, if you do that with many atoms, you get this, doing that, for instance, you change the speed of the atoms, you change the interaction time between the atoms in the cavity, you may get this sequence of events. And that's a beautiful sequence of events, okay? Because it shows that you start with a photon number distribution. And if you are measuring the photon number, you end up with an eigenstate of the photon number operator, just as quantum mechanics teaches. Okay? So that's a simulation of a measurement, actually. Okay? And it's a simulation of a continuous measurement. Now, it's interesting to realize that, each atom is just giving us information about the photon number. It's not changing the photon number because it's interacting in a non-resonant way with the field. So it cannot emit or absorb photons. So this is changing, not because there is an exchange of photons between atoms in the cavity mode, but because the photon number, but because one gives information about the photon number distribution by changing this interaction time between atom and field. We are probing with several atoms, and then we are getting more and more information about the field in the cavity, and we end up with a Fock state. So it's an interesting thing because you end up changing the field with information, because there is no interaction. I mean, besides the dispersive interaction, there is no exchange of photons between the atom and the field. Okay? So it's also an interesting example of the role of information, okay, in this field. Now, of course, since one knows the results of the atomic state measurements, we know if it was E or G, we can use this information to select the velocity of the next atom so as to maximize the decimation. Because, since we know the information, okay, I measure E, I know which ends were decimated. And I can use that to select a different velocity to decimate other values of n. So this process can be faster if we use this information. Now we can show that the minimum number of atoms needed to pin down the field is given by log basis 2 of the width of the initial distribution. Okay. Now, what about the phase? Well, as we measure the photon number, the phase is changed. In fact, you got an example of that in the slide I showed about parity measurement. Remember, when the phase shift was pi, by measuring a single atom, you make a superposition of two coherent states with different phases. Pi difference between them, and that's a Schrödinger cat state, okay? Superposition of two coherent states. If the phase is not pi, that will give you another superposition, but not with a pi difference of phase, other phase. So the first atom produces a superposition of two coherent states. When you send the second atom, each atom will give rise to kittens, or to second generation cats. It will also bifurcate. So at the end, you have something like that, not at the end, in the middle of the thing. And at the end, you have this circle completely filled with coherent states, which means that the phase is completely unknown. That's when you get a Fock state. Of course, if you have a Fock state, you don't have any information about the state of the field. Okay? So that shows that if you measure the conjugate variable to the number of photons, which is the phase, you get random results at the end. Okay? Now, so this is an example of the photon number phase complementarity. As you reduce the variance of the distribution and get to the final Fock state, the phase becomes completely unknown. And of course, as I have just told you, this is due to a successive generation of Schrödinger cats. Now, this is the experiment, that was done in Paris based on these considerations. It was an experiment on progressive field state collapse and quantum demolition photon counting. That's again the system that was used. In this case, they had a small field in the cavity, up to 7 photons. In fact, the probability of getting n equal to 8 was very small. Okay, so they had a coherent state in the cavity, but centered around the average number of photons equal to 3 point something, 3.8 actually. Okay? So they could consider that they have, with some error, up to 7 photons in the cavity. And then what they did was to, instead of changing speeds, they considered that the phase shift per photon is equal to pi over 4. So they calibrated the interaction time between atoms and cavity so as to get this phase shift per atom. Now, if you have this, you see that if n equal to 0, nothing happens to the atom. If n equal to 1, this vector in the equatorial plane, the spin along the equatorial plane will change its phase, and the phase will change by pi over 4 angles. So n equal to 1 is here, n equal to 2 is here, n equal to 7 is here, and then n equal to 8 will coincide with n equal to 0. Okay, it's a marker of the number of photons in the state. Now, so that's the idea, and the idea is the following: you start with a spin or two-level atom or a spin along Z. In the first Ramsey zone, you put it in the equatorial plane, then it goes through the cavity, and this spin can do one of 7 positions, okay, depending on the number of photons in the cavity. Okay. Now, but now you want to read the spin. What do? You again bring it to this Z direction. It's a sigma X transformation. So again, another transformation like the first one here. So you take it back to the Z axis and then you read it. Now, of course, when you read it, you don't get full spin magnitude as the projection, because, for instance, if you rotate the spin along this axis here, which corresponds to n equal to 1, different vectors here, when they go to the Z axis, will have different components along the Z axis, okay, if you rotate them along this. So different components. And and if you repeat this experiment over and over, you have different probabilities of finding these several values of n. In fact, the idea is to rotate along this axis, but not just this axis. You can rotate it along different axes, choosing the phase of this Ramsey setup here. Okay, so the idea is to rotate it, put it back on the z-axis, but to rotate it along different axes. And that's the equivalent in this respect to changing the speed of the atoms and probing the photon number with different values of the phase shift per photon. So that's the idea. Now let me show you the result of that, which is amazing, I find. So this is what is obtained. And if you look at this plot here, you see that it is assumed that initially probabilities of all photon numbers were equal, 1/8. Equal probabilities. Why? That means complete ignorance about the field in the cavity. If I start with a coherent state, that means that I know the state already. That's not fair. Okay? So complete ignorance. And then they just add the results obtained by measuring successive atoms. Okay? In this case, they have 110 atoms going through the cavity. The total time of measurement is 0.026, which is smaller than the damping time of the cavity. Okay, it's about 5 times smaller. Okay? And they keep observing the distribution, starting from this flat distribution as they detect more and more atoms, up to 110 atoms. And you see what happens with the distribution. There is this decimation process. At some moment, it seems that this part of the distribution will grow, but then it goes down. And finally, the one that survives corresponds to n equal to 5 in this case. Then they make another run, also with 110 atoms. And now the one that survives corresponds to n equal to 7. Now, if you make lots of runs like this, each run with 110 atoms, at the end, you have the probability of having five atoms, or 5 photons, I'm sorry, or 7 photons. This will give a probability distribution. Okay? So by doing that, you find the probability distribution of the field inside without exchanging photons with the field, which means it's a quantum non-demolition measurement. And you can reconstruct actually the distribution of photon numbers in the cavity. That's the result of the experiment. And this is a Poissonian distribution, which is consistent with a coherent state, okay, which you previously injected into the cavity, actually. Okay? So you see that you have some funny effects. You have these small things here, which correspond to incomplete collapse. In other words, because you cannot do this forever. You stop at 110 atoms, because if you keep doing it, you get to the damping time of the cavity, and then you don't have a good result. So there is a limit for time, and you have to negotiate that between having many measurements, but at the same time being smaller or sufficiently smaller than the damping time of the cavity. So these are incomplete collapses. And you see also that n equal to 0 here does not agree with the Poissonian distribution. Why is that? Remember that there was n equal to 8 there? It's a small probability. So, n equal to 8 will give you the same signal as n equal to 0, because the arrow will point out in the same direction. Okay? So you get an excess here, which is precisely given by the theorem. Okay? So this is an example. Also, you can calculate the average number of photons here. It's 3.46. And from that, you can evaluate the average number of photons of the initial state, considering that you have some decay. And the average number of photons in the initial state is 3.8. So there was a small decay. Now, finally, I want to give you some idea about the use of cat states for precision measurements. And this was based on an idea by Zurek. It was developed theoretically in this paper. And there was an experiment here done at Collège de France in Paris. Okay? Now, this is a superposition of 4 coherent states. And you see that there are interference fringes there. Now, these interference fringes come from a representation in phase space, which is the Wigner representation. How much time do I have now? Okay. Okay. So, and this is shown by the Wigner distribution. Now, I guess many people here don't know what the Wigner distribution is, or maybe know. Who knows what the Wigner distribution is? Yeah, I was right that many people don't know. Huh? And you know, I feel awkward to explain this to Suhail, Marlon, and Girish, you know, and maybe other people here too, I don't know, Bill also. And, okay, so sorry about that, but anyway. So let's talk about the Wigner distribution just for 2 minutes. Yeah. So suppose we want to have a phase space representation, which should be as close as possible to a classical phase space representation. So what do we demand from a classical phase space representation? Well, this is a distribution in phase space. So we have this momentum and position, Q and P, canonical variables. So if I integrate this distribution with respect to P, I should get the position distribution. That's called a marginal distribution. If I integrate with respect to position, I should get a momentum distribution. This is a density operator. Now, for those who have not seen what the density operator is, you can immediately translate this to a pure state. For a pure state, this means just the magnitude square of the wave function in position space. And this is the magnitude squared of the wave function in momentum space. Okay? So that's the minimum we could ask for a decent representation that should be close to a classical representation. Now, furthermore, I'm going beyond this minimum. This should be true if the axes are rotated, because there is nothing special about this axis. So in fact, this distribution should satisfy this condition here. Okay, I'm now rotating the axis, and if I integrate with respect to this generalized momentum, okay, in another axis, I should get the probability distribution for the orthogonal component in phase space, which I call Q of theta. Now, and I know that in quantum mechanics, the probability distribution of Q of theta is given by this expression. Again, the density operator. This is a unitary rotation operator that applies to Q. And so this is a rotated function. And this is the average value of this in the Q state. So this gives me the probability of finding Q of theta in rho. If you want U of theta applied to Q is Q of theta. It's the state Q of theta. And that's just the probability of finding the state. So you see, you have this expression here, which involves two equalities. The first one is a purely classical one. Okay, this is what I require from a classical distribution. Okay, I rotate the axis, and the marginal distribution should give me this result. But then there's a second part here, which is the quantum side of it. Okay, this P of Q of theta should be given by an expression like that. Okay? Two requirements, connected requirements. Now, there is a very interesting theorem that P of Q of theta, if you know this probability for all marginal distributions, that uniquely determines this function. Uniquely, okay? You should measure for all directions of P of theta. Okay? So, this is actually something which was known a long time ago. In 1917, this is called the Radon inverse transform, and that's the principle of tomography. Actually, you see that here. That's an X-ray tomography of some person, and what you do is the following: you rotate the person or the X-ray around the person, and you look at the transmission of the X-ray, and that's like doing a marginal distribution, okay? That corresponds to P of Q of theta. So if you do that for all directions, from this information, we can reconstruct in 3 dimensions the object that is being surveyed, okay? Now, in 1979, Cormack and Hounsfield got the Nobel Prize in Medicine for applying this principle to medicine, okay? Random transform to medicine. It's funny because, you know, Cormack was a physicist and Hounsfield was an electrical engineer, and they got the Nobel Prize in medicine, okay? So physicists, physics students, beware, huh? Lots of opportunities, lots of opportunities. You know, physics, you know, we don't say that everywhere, but maybe here you can, come on, it's the mother of all science, right? You know, physics in Greek means nature, right? So, okay, so that's it. So you can apply it in several places. Now, so P of Q theta, as I mentioned, is the marginal distribution. So, and this distribution, which is uniquely defined by that property, was found actually in 1932, not by this means, by Wigner, who was looking for quantum corrections to classical statistical mechanics. And the expression he had was something like this, okay? So this relates this Wigner distribution, this phase space distribution, with matrix elements of the density operator. In fact, you have here a Fourier transform of the density operators, of the matrix elements of the density matrix in the X basis. And Moyal in 1949 showed that this distribution can be used to calculate average of operators in symmetric form, like if these operators were classical functions. Very useful, okay, to do that. Now, since this is a Fourier transform, you can invert it and express the density operator in terms of this Wigner function. So knowing the Wigner function of a system is equivalent to knowing the density operator of the system, is complete information of the system, okay? Now, examples of Wigner distributions, that's the Wigner distribution for the ground state of a harmonic oscillator. Could be also the Wigner distribution for the vacuum state of an electromagnetic field. That's for the n equal to 3 state of a harmonic oscillator, or for a Fock state of the field with 3 photons. This is the Wigner distribution for a mixture of 2 coherent states. The coherent state is a displaced ground state, and this is a mixture of them, which means that you have a Gaussian state here and another Gaussian state here, and that's the picture of this mixture. And now this is the superposition of alpha and minus alpha, which is amazing, right? You have now interference fringes which come from quantum physics, and the Wigner function, this shows these fringes here. Now, this Wigner function has been experimentally produced, measured in ions, in cavities. For a trapped ion, Winans group measured that for the one phonon state of an ion. It's an ion in a magnetic trap, electromagnetic trap, and you see that's the Wigner function. And it has a negative part here, okay? So the negative part is telling you, come on, you know, I'm quantum, you know? I have all those nice classical properties, but, you know, I'm a quantum object, okay? So it can be negative. It's not a probability distribution. Now, and this, oops, getting to the end, and there are also measurements of the Wigner function in cavity QED. In fact, with Luiz Guilherme Lutherbach, a student of mine, we proposed a method for direct measurement of the Wigner function in cavity QED and ion traps. This was implemented in this paper here for the case of 1 photon in the cavity, and they found something like this, okay? I'm not showing precise, actually they measure a slice of this, and they can measure several slices because this object is isotropic, okay? Around the z-axis. So this was the experimental results. So we can measure it. And if we can measure it, then there is an idea that comes with it. Suppose you have now a Schrödinger-Cat state, superposition of 2 coherent states, and these are the interference fringes. Now, we would like to measure a small displacement of this harmonic oscillator of a field in the cavity. And what does it mean to measure it? Well, I would like to have this displacement so that the displaced state becomes orthogonal to the original one. Because if they are orthogonal to each other, then I can make the difference. I can find the difference. I can invent a method that distinguishes one from the other. Okay? Now, so the question is this: I want to displace this cat state here, and I want the scalar product between the displaced state and the original state to be 0. And I want to know how far I can go with epsilon, so that I can get orthogonality. Now we can calculate this. Again, another exercise for the students. And this gives me this result here. Again, you see these amazing fringes here with this term. And now I want this to be 0. Now it's easy. Cosine has to be equal to -1. So this epsilon here must be given by this value here. It involves the magnitude of alpha. And magnitude of alpha for a coherent state is equal to square root of the average number of photons in the state. Okay? So you see, epsilon here, this minimum distance that you can distinguish, is inversely proportional to the square root of the number of photons. Now, that's much better than using, for instance, a coherent state. For a coherent state, in phase space, it's like a ball with diameter equal to 1, order of 1, and then you want to displace it. Okay, and I'm also very proud about this animation. It was not done by a student, it was done by me. Anyway, so we expect them to be sufficiently far away so that you can distinguish both of them. And this distance for that to be true must be of the order of the diameter of the coherent state. I'm setting here h bar equal to 1. Okay, so the diameter is of the order of 1. So you see epsilon here is equal to 1. That's the so-called, or h bar. That's the so-called standard quantum limit. Now look at that. That can be much smaller than 1. Okay, as the distance between the two coherent states increases. So you see, by using this property of the fringes, I can increase my precision in estimating the displacement of the states. For a harmonic oscillator, this could be used to measure very weak forces. And in fact, this was analyzed in these papers here as a means to have weak force detection. And of course, if we use this state here, which Zurek called the compass state, we can do the same thing, but not just in this direction. We could measure small displacements in any direction. In fact, if you look at this chessboard pattern, I find this a beautiful Wigner function, right? Because you have interference between these two, and this is interference between the 4 of them. And this is a chessboard pattern. Now, if you look at this elementary cell here, the area of this cell is h bar over magnitude of alpha square, which is just the distance between these coherent states and the origin. So this is h bar over n bar. And therefore, this is the area. And therefore, the displacement along any direction by the square root of that is by square root of h bar over n bar, we can show, as I mentioned before, in the same way as before, implies orthogonality between the displacement state and the original state. You just have to displace it by the size of this cell. So it's an amazing device for quantum measurements of displacements. It's better than a coherent state, of course, and we can go beyond the standard quantum limit. In fact, we can reach the so-called Heisenberg limit of precision. Now, how do you do that? How do you do the experiment? Well, I'm not going to tell you now. Otherwise, I might be shot by the coordinator of this colloquium. But at the same time, I'm going to use it as a marketing device. I'm going to tell you how it is done in my next seminar, which is going to be held next Tuesday at IQSE, right? That's at this time, 11:30, okay? And there will be pizza before, right? There will be pizza before. So, in these times of economic crisis, students profit from that, should profit from that. So, so this was an experiment which was made again with these people. It was Serge Haroche's group. And in this experiment, we used that idea of having these small fringes to measure very small displacements of a field in a cavity. Okay? And in fact, we showed that you can beyond the standard quantum limit. In fact, you can get very close to the theoretical Heisenberg limit in this case. Okay, but this I'm going to tell you next time. Now, of course, I only talked about this kind of cavity QED. People are working a lot nowadays on circuit quantum electrodynamics. This is an interesting paper that shows the relation between the two. And if you want to learn more about circuit quantum electrodynamics, there is this review paper here, which is very interesting. And I have done some work on that, but much less than the work I have done on the cavity QED I have showed to you. And of course, I have to list here some of the collaborators. Of course, the danger of that is that you always don't mention someone. I know it's a risky business, but that's why I mentioned just Serge Haroche's group at École Normale Supérieure and Collège de France, especially these two guys, Jean-Michel Raymond and Michel Brun. Jean-Michel was a student of Serge, Michel Brun was a student of Jean-Michel, and they are great guys. In Brazil, I collaborated with Nissim Zaguri. It was my teacher of quantum mechanics, actually, at the beginning of the graduate school. Then I came to the United States. And then these are colleagues, Ruiné Matos Filho is a strong collaborator on quantum measurements and quantum metrology. Many students participated along this line of problems. There are other students who were involved in laser physics and things like that, okay? But so these are some of the students, and all of them now are professors. These three here are professors at the Federal University of Rio de Janeiro, and Antonio is professor on the other side of the bay. It's the other university, Federal University of the State of Rio. In the IQSC, I have had the joy of collaborating with Girish Agarwal on quantum metrology, Jiaxuan Wang, his student, very efficient, very nice. She has a very nice property. She finds my mistakes in calculations, fantastic, okay? And they're not few, they're not few. Anyway, Suhei Zubair, of course, collaborated also with me on cavity QED, and Marlon Scully collaborated on laser physics and on several other things, actually, and I do have very nice memories of my stay in New Mexico, and also Max Planck, which was an intense collaboration there. And I want to thank all the collaborators, especially those who are present for this. Thank you very much.
I start from one while you're
Yes.
up. But you started from this logic gate idea, right? It's the very beginning, which requires Fock state components. I wonder if this idea of interference between coherent states could be also used as a kind of multi-qubit gate.
Yeah, it can be. It can be. This has been proposed actually by some people, but my experience with that is that at the end, they do not work so well for logic gates or for quantum computing. But there are proposals of using them for quantum computing, certainly. I think Newborn has worked on that. Girish helped me, right? I mean, there are some papers by Newborn and collaborators on that. But I don't think people are doing quantum computers with that.
Or IQ or many more.
Yeah, the question is, is it possible to have a microwave cavity with that large Q with many modes? And you mentioned 1,000.
No,
a dozen. Oh, a dozen. Okay. No, 1,000. That's 12. Oh, it is possible. Sure, it is possible. Of course, the Q of the cavity defined for the mode. Okay, it involves the frequency. But as long as you keep frequencies close to that, you can have several modes, okay, of the field. In principle, yes, you can have it. Okay. Now, experimentally, you can do it. You can do it. You can. I mean, they don't do it because to do things with that becomes messy, okay? It becomes messy, but you can do it, you know. I did not think about that, but I can think about that now. So how can you do it? So how do you feed this cavity? You feed this cavity by coupling it with a microwave field. And that's produced by a microwave generator. And then you generate a microwave field with frequency equal to the mode you want to fill, okay? Now, you could also, you must do it quickly. Actually, you could change the frequency of the microwave generator and inject coherent states in other modes. It injects a coherent state because you see, the microwave generator is like a classical antenna. So it produces a coherent state, okay? So that's the way you put there. Another way, that's one possible way to put coherent states in more than one mode. The other way is to send, which is experimentally tough to do, very tough, which is the following. You start with a cavity in vacuum, and then you send atoms in excited states so that they can populate a mode of the field. Now, of course, you could choose the state of the atom so that other states will coincide with other modes of the field. And you could use the fact that you can have a Stark effect that could change the energy between the states so that you can feed other modes of the cavity. Now, if you talk about a dozen modes, I find that, experimentally extremely tough. You see why? Because you have to use atoms resonant with the field to populate that mode. And then if you have several modes, you have to change the states so as to populate the several modes. And that's tough to do. But, in principle, it is possible. 3, 4 modes. Dozen, I don't know. The experimental guys might get depressed.
So you have to go to the optics, from microwave to optics.
Yeah, right. Optics is easier to do that.
I know it's getting late, so probably we can just close the official part of the colloquium online. but if you want to ask more questions, go ahead. It's not here, you cannot escape anyway. So,
Yeah.